Okay, in last session we have been going up to page 100, so we are going to continue from page 100. Okay, so a brief review of from last session we talked about this Neyman-Pearson detector, which is a match filter. By match filter, we mean that we will design a impulse response for this block, impulse response for this block, and that is the uh, flip version of the flip around version of the signal, and this is under the known signal assumption. So if you have a signal like this, then you're going to have a impulse response like this. It's a flip around version or time reverse version. And when whenever we have a match detector, in this case we have a match filter detector. We are always interested in its performance. Remember that of uh, the design of a detector is something important, and also the other thing that is important is to derive or discuss the performance of the detector. That's also one of the important part of this class. And of course, in many cases, people are always interested in the performance. So for example, if you uh, take machine learning as an example, you uh, you train the machine, then you come up with a machine with a lot of parameters. Then the next thing you do is you try to figure out either by empirical testing or by analytical derivation, you would like to know the performance of the machine, right? So in this case, now we come up with a detector which is the match filter detector. That is something like this. Then we, of course, when we have illustrations for that, and then the next thing is we are going to be interested in its performance. And recall the idea that we talked about before. We mentioned that uh, there will be an idea that is the so-called ROC, receiver operating curve, which will be the PD versus PFA, right? And of course, you have another thing. You have four combinations, right? Uh, PD is that when the truth is H1 and your decision is H1, you get a detection, and that's called PD. And when you have a H0 as a truth, and then your decision is H1, then you have a false alarm. False alarm, that's PFA. So PD versus PFA, then the that will be um, the so-called receiver operating curve ROC. ROC. Okay, so so now we will start from the match filter detector. Of course, then there will be other names such as replica correlator or whatever name it is. It doesn't matter. The point is we are going to have this x multiplied by signal s and then do the summation as a so-called test statistic. Then when its gamma is larger than a certain threshold gamma prime, then we will decide H1. That is our detector. And of course, this is derived from the likelihood ratio. In fact, this is also the maximum likelihood detector. It's just a consistent. It's just a coincidence, consistent with respect to each other. So, uh, before the end of this class, I think we are going to have multiple hypotheses. By that time, it will be more clear what we mean by maximum likelihood. So, under either hypothesis, Xn is Gaussian, and since this T of X is a linear combination of the Gaussian random variables, then Tx is also Gaussian. Recall probability theory. Uh, this is a nice property for Gaussian. When you have linear combination of Gaussian, the outcome is going to be Gaussian again. So this is sort of a very nice property for Gaussian. But not every random variable has such property. Some random variables, when they are added together, they may not be the same as they were before addition. But Gaussian is, so this is good. Um, so we have Gaussian random variable as t, right? This t is Gaussian, and then we will start to sort of calculate the expectation for t. So the e means the expectation. This e here is the expectation of t under hi, and variance of t under hi. So that denotes the expected value and variance of t under hi. So let's see. You have expectation of t condition on h0. So you just write it out. If that t is under h0, then what is t? Recall, just a little bit of recall. Under h0, this is page 95. If you'd like to follow the page number, this is 95. Okay, you come back to here, then you see h0 is actually the w. h1 is s plus w. Okay, so this is the signal model. Okay, and then we go to here 101. Expect of t under h0. As in page 95, if it's under h0, then t is going to be just w, right? And then t, uh, I'm sorry, t is x multiplied with s, but that x is only w. So w, t becomes w multiplied s. And when you are trying to expect this Gaussian random variable with the s, that s is constant. Okay, this is a constant, but this is a zero mean. So when you take the expectation of this whole thing, it becomes zero, because this is a constant. You can take it out and it becomes expect of summation of omega w, but w is zero mean, so the outcome will be 0. Then this aspect of T condition on H1 will be a little bit different. Recall what we just see. I'm not going back to 95 again, but you can check 95, page 95. Under H1, that X here is going to be a signal plus a noise. As a result, it will be S plus noise and then multiply with this S and it goes here. And then you do the summation. And what happens here is you are actually having expectation of S multiplied by S and then expect of W multiplied with S. But that W multiplied with S, this part, when you take the expectation, that is 0. As a result, you are going to have expect of S multiplied by S, and that's S squared, right? So you expect summation S squared, which is what? It's the signal energy that we have mentioned about in that session, in our last session, right? We say something about signal energy, and that's S squared. And then you do the summation, you get that signal energy, and we call it epsilon here, the capital epsilon. And then the next thing is the variance. For the variance, we are taking variance of T of condition on H0, and then that's variance of W because condition on H0, T is only W multiplied by S, with is the same as this one, So we are taking variance of it, and then it becomes, when you are taking variance, it actually depends on only the random variable. So let's take a look what the random variable is. This is a random variable. The W is a random variable. S is what? S is a constant. So S is not a random variable. So when it goes out, it becomes 0. No, excuse me. It becomes square. When a random variable is multiplied with the constant and is taken variance, the constant can be taken out with square outside of it. That's the identity in probability, and that's a probability identity. So that S goes out, becoming S squared, and this summation actually goes out of the variance. This is also a the probability identity, right? When you are trying to take, for example, if you are taking a variance for A plus B, what happens is you are taking variance of this random variable and this random variable, and the outcome will be variance of variance A plus variance of B, under the assumption that A and B are independent. So here we have a summation of this W, but that W is independent for different n, right? It's independent for different n values. As a result, we can take the summation out. That's under the assumption that Wn are all independent with one another on the different n. So, and of course, just uh, that is just the assumption of the model, which is uh, uh, which is in page 95. If you, well, you'd like to review a little bit about the model in page 95, you see that we have assumption about independence for this W. So that summation goes out, S squared goes here, and then you have only the variance of W because this is the only random variable inside it. As a result, you have a summation that goes in, and you have S squared, S squared with the index n. And then variance of this is what? This is simple because we have, again, in page 95, signal model, we have assumed it to be sigma square. So this thing becomes sigma square, and summation corresponds to only S of n because the summation is over the index n, and then we have S squared, we also with index n. So this becomes here, this goes here, and summation with this as stays. And again, this is like the signal energy we mentioned before. So this is the energy. We call it epsilon. We call it epsilon here. So we have sigma square epsilon. Okay, so now we have expectation of this, and then variance of this under H0. And then of course, one more thing is we, as you can imagine, we calculate expectation under H0, H1. We have to calculate variance under H0 and H1. So now we come to page 102. So when you start to look at variance of that test statistic under H1, it's going to be sigma squared epsilon. And this is a similar process as this one. We just go through the same derivation, and then we can get something this like this. Unfortunately, this term is identical with this term here, with this term. So in other words, the test statistic has equal variance under H1 and H0. So now we can write it out. T is distributed. This notation means distribution. So T is distributed by Gaussian distribution with zero mean under H0 with this variance. And then it's epsilon as the mean because this has been derived here. And then the variance is sigma square epsilon under H1. Okay, so now we have the expectation and also the variance. Okay, so if we just show it out in figure 4.4, then we will see that you have zero mean. Right here we have zero. It's unwritten here, but we know it's zero. That's the probability density function of T. That's the probability density function of T under H0. And it has a variance. Variance actually represents the sort of the degree of spreading out, right? 就是它扩张的程度，这个 PDF 扩张的程度。So sort of the way it's spreading out. When you have a large variance, you have a wider distribution. When you have smaller variance, you have a sharper distribution. So that's the uh, idea, the illustration. So, but in this case, we have zero mean and then some kind of some kind of variance, which is sigma square epsilon. And then we have probability density function of t condition on h1, which is epsilon as the mean, and then with the same variance. So it's spreading out with sigma square epsilon. So of course we can do some change of variables. For example, here the scale test statistic t prime. If this is artificial, again, this is artificial, meaning that we do it intentionally, not not it it's not something sophisticated. No, it's not. It's just a change of variable. Okay, so we are changing variables here. T over this sigma square epsilon. How come we can do that? Have you ever think about it? When we are doing change of variable, we have to do it by parameters that we know. So if you go back to page 95 and review the signal model, sigma square is assumed to be known, and S is assumed to be known. So the epsilon, which is the signal energy, is assumed to be known. So when we are doing this change of variable, everything is assumed known. So we can do this t divided by this square root of sigma square epsilon as t prime. It's a new notation. Then it has the PDF like this. The reason for that is, if you think about it, you do t divided by this, then you use your proper what you have learned in probability theory and think about it. Uh, do the derivation. You find that this t prime has 1 as the variance. And when it has 1 as a variance, it gets us easier to go with the Q function. So, right, it goes with the Q function because we need variance to be equal to 1. That's the reason we do that. So we do this change of variable. We get this new test statistic that is T prime. And it's distributed with Gaussian distribution 0, 1, or Gaussian distribution 1 with this as the mean. You divide this with this, then you get this as a new mean. That is the new mean. So it follows then that the detection performance must increase with this or with this, since epsilon divided by sigma square is the mean, right? So think about it. When you have two distributions with variance equal to 1 and variance equal to 1, and then you 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 sort of like to have both of them more separated, then how do you make them separated farther and further away? You increase you increase epsilon over sigma square. So it's sort of like this formulation is giving you more insights, right? Because if you make them more separated, for example, this guy goes here and this guy goes to the right hand side, then they are more separated. And once they are more separated, you have better performance for sure, right? So uh, with this epsilon over sigma square, you like to increase this, meaning that you like to either increase this epsilon, or you decrease sigma square. You decrease sigma square because it's in the denominator. It's in the denominator. So as this whole parameter increases, the PDF retain the same shape but move further apart. That's the point. Move further apart. So uh, we can calculate this for PFA and PD. I think it's time we take a break. So we'll come back in a couple of minutes.